Toward the cloud. I don't know that one. Uh-oh, how do I? Oh, there it is. Yeah.
Got it. And I could also go here to more.
Okay.
And click hide. Yeah. Hide floating meeting controls. Yeah.
Okay. The hush fell over the room, right? We start early, or you want to wait till the time? What's that? Sure, that's fine. Go right ahead.
All right, everyone, thank you for coming to Reflections Projections. This is our very first speaker event, and you're going to be hearing from Todd, who is the chief architect at Oracle Tuxedo, which is one of the most widely used enterprise blockchain applications. And Todd is a veteran when it comes to transactions and blockchain and that sort of thing. He has over 40 years of industry experience. So we hope you guys learned something new by coming here tonight. Right.
Thanks, Alan. Thank you. I get started being hustled. So, yes, as Tom said, I'm the chief architect. It's actually for the Oracle transaction processing products, of which blockchain is one of those, as in Tuxedo is one of those, and the new product I'll talk about a little bit. So for the intersection of those. So, as I said, the talk is labeled from transaction to blockchain and back. And it's a little bit about sort of my career path, and starting here at the University of Illinois, and then finally ending up at Oracle and working on these different technologies over time and seeing the evolution of these technologies. No. Sorry. I think there seems to have stopped in this one. All right, we'll do without it. Oh, I know, because never mind, it should be fine. It's where the mouse was, what window was focused. Sorry about that. I'm not used to quite so many monitors. So what I want to cover today is a little bit about my background. So I started here at the University of Illinois. I'll talk actually a bit before that. Then talk a bit about transaction processing platforms. Then get into distributed transaction processing protocols, and then going into blockchain. And I'm assuming it sounds like all you guys probably know about blockchain, right? Maybe teach me a little bit. Would that be good? Maybe not. And then I'll talk about sort of the intersection between the two, about blockchain and distributed transactions, and some of the issues that can be addressed by combining the two technologies. So as I say, I started here at the University of Illinois in CS in the fall of '73. It took me a little while to graduate. I put myself through school working, and as an undergrad here, these are some of the organizations I worked for. So I worked for the Army Corps of Engineers up by Mattis, the Radio Research Lab, Radio Location Research Lab. Have any of you guys seen that huge set of telephone poles out southwest of here? That's called a Woolweber antenna array. And I worked at that lab basically to do radio location finding, trying to find things like subs and stuff like that. This was height of Cold War. And then I worked with Plato. Is Plato still on campus? Anyone know? No, no, gone. Okay, that was a learning system running on a Cyber 6400 series processor. Searle, the computer-based education research lab, worked there. I worked then dropped out of school, started for a small startup called Information Technology Limited. And what we did is we took the technology that we had built at Searle using plasma displays and microprocessors to be able to build intelligent terminals, which sounds silly in today's world. But back then you were talking about, your interface to a computer was either like a teletype or, a dumb terminal, basically a shell script or a shell prompt is all you got. So what we did is we combined microprocessors, LSI 11 from Digital Equipment with a plasma display And then that technology was purchased by Science Applications International to be used for militarized display purposes for things like in helicopters and stuff. I finally finished my degree in December of '81. And we started working with digital equipment. There I was a software consultant working in their consulting organization for 15 years. Well, not all of it. Some of the time was also spent doing some research. We built a distributed object-oriented runtime system. So you could build objects in assembler, you could build them in BASIC, you could build them in other programming languages. And then we built a system that provided distributed garbage collection, distributed method and invocation, stuff like that, when object-oriented programming was really the big thing. Got acquired by BEA Systems, and that's when I started working on Tuxedo, which is a transaction processing monitor. And I'll talk a little bit about those. And then finally, in 2008, BEA was acquired by Oracle. So I've been with Oracle since then. So I survived 2 acquisitions, and I'm still here. So introduction to transaction. I say I don't know what's being taught anymore, and I don't remember what was taught when I was here. To be honest, it was 40 years ago. So if this is completely redundant to you, tell me speed it up or whatever. So what is a transaction? Transaction fundamentally is trying to achieve an atomic unit of work. So multiple things happening, and they all either have to happen or none of them need to happen. So examples would be in a database. As you update 2 different tables in a database, you want those both either updated or neither one of them updated. Now every database system provides this, right? It's just built in, and typically they get started automatically for you. So as soon as you start interacting with the database, it creates a local transaction. Any tables you update all get updated as part of that transaction, and either they all happen or none of them happen. Messaging systems also provide this capability. And as I say, the whole goal is that all the updates happen or none of the updates happen to try to ensure consistency. As an example, banking. You don't want, if you do a withdrawal and a deposit, you don't want the deposit to succeed unless the withdrawal succeeded or somebody got some free money somewhere. And I say these are mostly provided most database systems, most messaging systems. And we refer to these as local transactions because they're typically only dealing with a single source of data, like a single database or a single messaging system. And a single connection, and I'll explain that in a second. So a little bit about transaction processing. Let's say a lot of my background is around transaction processing. So these are simple explanations. System takes a request, does some processing, generates a response. Right? Pretty simple, straightforward. Execute some business logic in there, which typically means updating some databases, maybe updating some messaging systems, whatever. And really, what these were early versions of what people are now calling application servers. So things like WebLogic, WebSphere, Tomcat, JBoss, those sorts of things, mostly all Java application servers, but there are other application servers besides Java. And these things were very similar to that. They weren't typically language specific, and they didn't have a lot of the frameworks and capabilities that these current application servers provide. As far as transaction processing platforms, IBM dominated this space for a very long time. They started this space basically in 1960, working with American Airlines to produce the Sabre system, which is the airline reservation system still being used today by many airlines. Then they created something called INS, which is a transaction processor, and as well a hierarchical database, IMSDB. CICS, Customer Information Control System. You see these green screens around, still at some places, those are probably still running CICS applications. So they talk to a 3270 green screen, although CICS has matured a lot. Oracle acquired Tuxedo from Novell, who acquired it from USL, who acquired it from AT&T. So it's gone through a whole bunch of acquisitions. It got started though in Bell Labs in 1983 to take an IMS application they had and move it off the mainframe onto a mini computer because the cost of the mainframe was so high. So Tuxedo was originally designed as a replacement for that. And then another one, ACMS, is one that Digital Equipment produced. So distributed transactions that take more than one source of the data, right? So, and these are called resource managers. And so what happens is you have, often it's for, as I say, 2 or more resource managers. It may be 2 or more clients to the same resource manager. So you might have a connection from 2 different application servers that talk to the same database, but most databases don't allow you to share that local transaction. The only way you can share that is using something like an XA transaction where you can detach from it and reattach to it from a different connection. So say the resource managers, they can be different database systems, they can be different messaging systems. It's a very common use case is take a message off the queue, do some update to a database, put another message on a queue, and go on to the next step. Now the thing is though, to get this to work right, you need a protocol for this all to work. So distributed transaction protocols are designed to try to solve this problem. How do I get these updates to either all occur or none of them occur? And fundamentally, this is a consensus problem, right? Much like the consensus problem that Bitcoin and other blockchain platforms are trying to solve, distributed transactions are a consensus problem. How do I get all the participants to agree on the outcome of that transaction? And so the thing that's a little bit different though about this consensus problem versus sort of the generalized consensus that you see in things like Raft or other protocols like that is that every participant can veto. Okay, so it's not like with the majority of votes, because if you had a majority of votes and only some applied the updates and the other didn't apply the updates, it'd be a total mess. So and the idea behind this veto is to saying, I cannot perform the action you're going to ask me to do next. So like a two-phase commit protocol, I'll get that in a second. So as I say, most distributed systems, they all have to agree on success. Any failure can veto it. This is typical, not always the case. So when we talk about eventual consistency, you'll see that we give up some of that those restrictions, but we also gain a lot of other problems. And I'll talk a bit more about consensus shortly. Multi-phase commit protocols. So these are fairly common. The most common one is something called XA. You guys, who's here done anything with an XA resource in Java? Anybody? Nobody. Okay, that's good to know. So in XA, it's defined by the Open Group. This was a standard that was designed or developed in the early 1980s. And actually, the design for this protocol came from the Tuxedo system that AT&T was building. So about the same time they were building that, they were working on this standard. And a lot of the ideas came from Tuxedo. So it goes through these phases. The first phase is a prepare phase. So somebody, typically something called a transaction coordinator or transaction manager, asks each of the participants to prepare. And what prepare means is saying, we need you to make sure that everything is set. When I ask you to commit, you'll commit. Okay, if you can't guarantee that, then you have to come back and say, I can't prepare, and the transaction fails, basically, it gets rolled back. If they can commit, then you move to phase two, if all the participants commit. And then at that point, then the transaction manager logs that commit decision in what's called a commit record, and then broadcasts that information out to each of the resource managers to tell them to commit. Okay. And I'd say it's usually resilient to basic failures. There's certain network partition failures and others long-term failures that two-phase protocols can't address. And so that's where these three-phase and more phase protocols, but personally, I don't know of anybody using any of those. Basically, everybody uses a two-phase protocol. And the key part here is that it provides ACID properties. So ACID is atomicity, all or nothing. Consistency is that this system moves from one consistent, all the systems together, all the resources move from one consistent state to another. You don't see a partial update by one and not the other, right? And so this is done typically through locking and stuff. Isolation, meaning that the effects of one transaction, if serialized, would have the same result as if they're operating concurrently, right? So it's a serializable property. And then durability. And what this means is that once the decision of the transaction outcome has been made, that decision is durable. So it can be recovered, you can go back, if even the transaction coordinator fails, it has a persistent log of that information. And so it can recover that to be able to tell the resource managers the outcome of the transaction. And that's a very simplified view. There's a lot of failure scenarios you have to take care of and stuff like that. The protocol takes care of all that. So eventual consistency is a relatively new idea. It's also called sagas. And Eclipse has created a standard for this, at least for in microprofile, called long-running actions. And the reason sagas came about is because at the prepare phase, the resource managers have to lock the resource. They have to lock whatever data was accessed, because they have to be guaranteed that it can't change until the actual transaction commits. And so that potentially causes a scalability and performance issue, because if you have common resources that are accessed by many different transactions, they all get serialized because of the locking. Eventual consistency says, skip the locks. We're not going to do locks at all. What we're going to do instead is we're going to do a bunch of simple little independent transactions in each of the participants. And then what we'll do is we'll say, okay, if we're successful, complete this transaction. And now that's left up to the business code. You have to decide, what does it mean to complete whatever the transaction was that you were part of? What does that mean? Does that mean unreserving something and putting it somewhere else? What, you know, and all up the application. And as well, the one that's really key though is sort of the compensation action. So completion actions typically aren't very difficult. Compensation might be extremely difficult. A simple example is, because there's no locking, I deposit some money in an account as part of one transaction, right? I then have another transaction that withdraws that amount. That transaction completes because it's all using local transactions, so there's nothing blocking this. Now the original transaction has to compensate. Well, where's the money coming from? The money's already gone from that account that you need to compensate, right? So eventual consistency works for many applications, but you need to be very careful because, say, the completion and compensation logic can be extremely difficult or maybe impossible, as in that case, right? What do you do if somebody withdrew all the money from that account that you need now to put back in the account that that you withdrew the money from? So another transaction model or protocol is something called try, confirm, cancel. I think this came from Alibaba. And it's a great transaction protocol for things like making reservations. So making car reservations, hotel reservations, all those sorts of things. It basically consists of two phases. The first phase is the try phase. And what the try phase is, these are all, by the way, is based on HTTP verbs. So you post to a resource manager, but some participant basically, and ask for a reservation. And it gives you back a URI. That's the try phase. So the client here, the actor, makes all those reservations and then says, I either want them or I don't want them. So either confirm them or cancel them. Well, you've got a URI, you've got some HTTP verbs, the transaction coordinator or the application itself simply just says, you know, put, or delete to all the participants. Okay, so it's a very clean, simple protocol, but this is not a generalized distributed transaction protocol by any means. Blockchain, introduction to blockchain. You guys probably know more about it at this point maybe than I do. I don't know. Yeah. This certainly wasn't taught when I was in school. So blockchain fundamentals, right? Hopefully everybody knows what, at least this part of what a blockchain is all about, right? It's distributed ledger technology, right? To decentralize. Well, yeah, we'll get into decentralized versus distributed in a minute. What happens is you have a block, and initially what you have is called the genesis block. And then as each block, which may contain transactions or may not, it depends upon the blockchain platform. And then the next block that gets added includes a hash of that block. And likewise, the following block includes a hash, includes a hash, includes a hash. Which that means is that as long as you have the genesis block, you can tell whether any block was ever modified or not, right? Because you just simply follow and say, does this block have the right hash? If it doesn't have the right hash, it's not.
Could you explain what a hash is?
Oh, okay, I'm sorry. A hash is a mathematical function that takes a large amount of data and compresses it, not compresses it, but maps it to a much smaller amount of data. So a typical thing would be is a 256-bit hash. And so if you have a block of data, you can run this hashing function, and there's a variety of them. It can produce a 256-bit number that almost guarantees that if you change anything in the original block of data, that hash will change. Right? They call that the pre-image. So if you change the pre-image, then the hash is going to change. Now, that can't be guaranteed, right? Because it's possible you can change enough bits to still get. In fact, that's sort of what the whole proof of work mining is in blockchain. Okay, trying to find a pre-image hash that effectively maps to a certain value or less than a certain value, so it turns out. So that's what a hash is. So this block containing a hash of this block means that when you check this block, you can say, oh, does it have the correct hash? Yes, and this block's okay. And I can go back and go to the next blocks and so forth. So I can validate the whole chain of blocks and make sure that no data has been tampered with. Now people call this immutable. I don't like using that term because immutable implies it can't possibly be changed. This is just data stored somewhere, right? Data stored anywhere other than maybe a read-only memory can be modified. But it's tamper evident is the term I think is probably most appropriate, which is what most people are concerned about. They want to know whether the data was tampered with. And then, so you have this chain of blocks, blockchain, and then you use consensus, meaning getting to agreement about what data goes into the block and what the next block is. That's the whole problem that blockchain is trying to solve with these different protocols. So as I say, consensus is how do I get a bunch of things so things to be able to agree. And what makes this particularly difficult, oh, thank you for water, is that most systems are crash fault tolerant, meaning that if some part of the system crashes, you can recover from that through retry mechanisms, through lots of alternate sources of data. There's lots of different solutions to that. There are also, though, faults where they're called Byzantine faults. And a Byzantine fault is typically referred to as there are malicious actors involved in the system. And it comes from something called the Byzantine generals problem. Byzantine generals problem was a proposed problem to be solved. And it basically is, you have a city and a bunch of armies that are trying to decide whether to attack the city. And the armies don't trust each other. The generals in the armies don't trust each other because they're different armies. And they all have to attack, or not all, but a majority of them have to attack to be successful in their attack. If less than a majority attack, they'll get wiped out. Okay, so it's very important that they get this answer right, that all the generals either decide to attack or they don't, none of them attack. So that's it. And the problem you have is that generals may be dishonest. They may tell one general attack and the other general not to attack because maybe they want that army to get destroyed. Right? So the generals may lie, the messengers may lie, the messengers may not get the message there. There's all these kinds of problems that can occur, but it's these malicious ones where somebody's actually trying to break the system that are these Byzantine actions, and those are much, much harder to protect against. So, as I say, it depends, the protocols that are available depends largely on this one factor, which is how many participants. Are there a known number of participants? If there's a known number of participants, you can use things like voting and all that sort of stuff. If there's an unknown number of participants, how do you decide, how do you prevent them from, making a mess of things? How do you prevent Byzantine actors in that case? What's a protocol you can use if you don't know the number of participants? We'll talk about that in a minute. First about, crash fault tolerant consensus protocols. So these are used heavily, right? Because many systems don't require protection against Byzantine actors. They don't require Byzantine fault tolerance. And part of the reason for that is that Byzantine fault tolerance is expensive typically. The protocols involved require a lot of interactions. It's not a trivial problem to solve. In the crash fault tolerant protocols, the two most popular probably are Paxos, which is one of the original protocols. And there you have a proposer, and they create a number of proposals for changing the value of a key. And then they send that out to what they're called the acceptors. The acceptors then will only accept that if the proposal number is greater than the proposal number that it's already received. And then finally, there's learners who basically decide, yeah, this value now is final for this particular key at this particular proposal number. Another protocol is Raft. Raft is much simpler in many regards. Essentially, what happens is who's controlling the decisions about what goes into the transaction log or what actions are going to take place is controlled by a single leader for any given period of time. And then if that leader should fail, or if somebody decides that leader is not acting properly, then they force what's called a leader re-election, and another member of the cluster or the group of nodes gets elected as the leader, and then can take over and provide the ability to provide consensus on the log. So yeah, that's RAT. This is used by things like Zookeeper, etcd. A lot of those clustering kinds of software make use of this. Which also, by the way, tells you that these are not Byzantine fault tolerant. So if you're using those and you've got bad actors in your system, you potentially have a whole heap of problems, right? Because this has no way of knowing whether somebody in the cluster is misbehaving. So then you have these Byzantine fault tolerant protocols. As I already explained, the general problem. But as I say, the sort of more technical, not technical, but a better definition of a Byzantine fault is any fault that exhibits different systems to different symptoms to different observers. Okay, so that's like telling him to attack and telling him to retreat. Right, two different observers, two different answers for what's supposed to be the same answer. Leslie Lamport proved that for Byzantine fault tolerant protocols, if you have one, you have to have a known number of participants, and you need 3n, where n is the number of Byzantine actors participants. So if you have 2 Byzantine actors, you need 7 nodes to be able to prevent them from being able to corrupt basically the system. Common implementation, so PBFT is a very common one. Tendermint, hot stuff, these were BFT. This is a huge area of research, by the way. And if you search online, something I will warn you about is that there are an awful lot, especially in the blockchain space, there's a lot of people claiming their protocols are Byzantine fault tolerant and yet have no proof for it. Or the proof is some white paper that is hardly a proof. There's only very few that have been using proving tools basically have been proven to be Byzantine fault tolerant. Okay. So when you have an unknown number, the problem gets much more difficult. And this is sort of the problem that Satoshi Nakamoto basically solved by combining a bunch of existing technologies to create Bitcoin. Right? So Bitcoin uses something called proof of work. Proof of work is a way to randomize who gets chosen to be able to choose what transactions are placed in a block and what's the next block. Right? So you can't use a random number generator, right? Because people just cheat. Right? If you say, okay, wait a random number of seconds, I'd say 0, I get the next block. Okay, and I get a reward for that, at least in Bitcoin mining. Right? So you get some reward for that. So you want to be able to randomize this to prevent any one or any small group of participants from being able to control the outcome of the blockchain. Right? Because if you don't do that, people are gonna mess with you. And there've actually been some of that. Here's the next. So the thing is that the nodes doing the work, who decide, who want to choose what transactions go to the block, there's only certain things they can do. They can't modify the transactions because the transactions have a digital signature, right? So those digital signatures can be verified, and you can prove that the transaction has not been modified. You can prove who the transaction proposer was, or who provided that transaction due to the signature. But what they can do is what's called censoring. So they can say, oh, I'm not going to process your transactions. Who knows why? Maybe because you're a competing company or something like that. But so they can censor, and they can also what's called front run. And front running basically means is that they put some transactions in front of others for the purposes of making sure that they get executed. Maybe it's because it's you're doing foreign exchange, and that where transactions happen very quickly. And when somebody's transaction gets in front of another, they get more money than the other person gets. So there's some front running that front running can possibly happen, but you can't change them. And essentially what proof of work does is it randomizes who's going to make the choice. And the way it's done is, remember that hashing function I talked about? So the miner takes a block of data, modifies it a little bit, or takes a block of data, hashes it, and they have to come up with a hash that has a certain number of leading zeros, meaning technically it's less than a certain value. So if they find that, then they get to claim what transactions go in the block and what the next block is, right? And they adjust this difficulty, and this is very difficult. I mean, these hashing functions take, I don't know what the current number is, but a typical hashing machine can do definitely terahashes in a mining rig, I think at this point. I don't know what the actual numbers are, but it's, then people build special processors just to do this kind of mining, just to do this hashing. And so they do this because they get the reward. But the difficulty is that multiple nodes may do this nearly simultaneously because the network's distributed. Right? You've got this vastly distributed network. I solve it, and one solves it, he sells it, you know, a tenth of a second later, but we're on different sides of the country. I don't know about the block he produced. He doesn't know about the block I produced. So we both create a block and we create a fork, because we both create what now is the longest chain. And then somebody will build on his chain and somebody will build on my chain. And eventually one of them will get long enough and it will become, essentially that will be the ending main chain. And the other one dies, goes away. All the transactions that were in there basically go away. So this creates another problem. It creates what's called a finality problem. Finality is when are the results of a transaction guaranteed to never be undone. Now, in normal transaction processing system, that's as soon as the commit has been done. Once the commit has been done, there's no question about it. Everybody has that data. In Bitcoin, if one of your transactions is in one of these abandoned forks, your transaction didn't get executed. Now, that doesn't sound so bad because you can simply resubmit the transaction and you make it into, or somebody else, I'm sorry, it still stays in the transaction pool. It'll get a block eventually. Oh, that's not right, I'm sorry, it has to be resubmitted, I think. Anyway, I'm not a Bitcoin expert, by the way. But let's say this finality problem is, let's say I paid you $1,000 for a Bitcoin, and that transaction on the Bitcoin network, that transfer from you to me of that one Bitcoin never happened because it was ended up on one of these other blocks. I'm out $1,000. So finality is critical, especially in financial transactions, which I find is interesting that Bitcoin has this problem. So, you know, so when does it become permanent? Well, never is the true answer, right? If you have sufficient computing power, you could completely rewrite the Bitcoin blockchain. Completely. You could, which is a little staggering, but it's theoretically possible. The amount of power processing hashing power you need is absurd, but it is possible. And so you also then have to wait. And so you wait, because the longer you wait, the longer the chances your fork is going to be the one that remains. And how long you wait depends upon how fast the blocks are created, how fast the blocks are disseminated. So in Bitcoin only does one transaction every 10 minutes, at one block every 10 minutes. Right? Ethereum does 7 or 8, something like that, or maybe 15 or so, I think, maybe blocks in a minute. And so what happens is they tell you in Bitcoin, if you want to be pretty sure that your transaction is going to remain, you wait an hour. In Ethereum, it's not quite so bad, maybe under 10 minutes. But again, there's no guarantee. If you're moving $1 billion, I'd like a guarantee, but maybe some people don't. There's another problem here too, is that what's called a 51% attack. If you have enough proof of work miners, more than half, you can then control basically the blockchain. And that has happened 3 times already on Ethereum Classic. So enough miners got together and said, we're going to modify the chain, and they basically undid transactions that have been done to their benefit. Okay. The other thing, and this is why I'm not a Bitcoin lover, this is one of my biggest beefs, I think, at all, is the amount of energy that consumes. So Bitcoin mining is estimated this year to consume more electricity than Venezuela or Norway or several other countries. About, let's say, 150 terawatt hours of electricity per year. Just to process one transaction takes 700 kilowatt hours. One transaction, 700 kilowatt hours. I say that's what about an average house uses in a month. It's not sustainable. But anyway, so decentralization. This is partly what blockchain is, not mostly, but largely about. Decentralization is the idea that there's not one single organization or entity in control. I've got multiple entities in control of whatever it is I'm controlling. Whether that's transactions, whether it's Bitcoin, whether it's my blockchain, whatever it might be. The idea is that I don't want one organization controlling stuff. So there's an example of VisaNet, which they say they can process about 76,000 transactions a second versus Bitcoin's 7 transactions per second. A little bit different in scale there. That's decentralized systems don't perform well, but But the big advantage, by the way, one of the big advantages of decentralization is improved security. If a hacker hacks VisaNet, the VisaNet systems, they can do virtually probably anything, right? If they have to hack a decentralized system where you've got 5 organizations and they're all cooperating together to replicate the data and agree upon the changes of those data, you would have to attack 3 of those systems, compromise 3 of them to change the outcome, right? Attacking 2 would probably not be enough, depending upon your consensus protocol. So decentralization is good in some respects. It causes difficulties in others. As I say, it's really a spectrum. Is it 2 organization network? Is that a decentralized network? Some people would argue yes, some people argue no. Some people say Bitcoin is completely decentralized. Well, it's not really. Miners, these people who buy these mining rigs or whatever, they almost all are part of what are called a mining pool, because your chances of winning are like winning the lottery. And chance of getting a block. So if you and all of your neighbors go into a lottery and you buy a bunch of tickets, you improve your chances of winning, right? But you then have to split it up, right? The routines from that. Same thing happens in Bitcoin. The mining pools, basically, they come together. And if you happen to be part of that mining pool and you get the Bitcoin mining reward, it's shared across everybody in the pool, okay? So one can argue that with 3 of the mining pools controlling 60%, if those 3 mining pools got together, they could easily perform a 51% attack. There's some other things about why it's not decentralized either. Like, it's not decentralized in terms of its development. There's just a small number of developers. Anyway, a little bit more about blockchains. So I like to refer to them as 2 different major categories. There's permissioned blockchains, which most people don't know about, but sometimes called enterprise blockchains or sometimes called private blockchains. I'm not a fan of using private or public because those have a whole lot of connotations that aren't related, right? What's related is, do you require permission to be able to be a member and use the blockchain or not? So permissionless, like Bitcoin, is anyone can participate and valid. They're often anonymous because they're signed by some key that you hold in a wallet. So you can prove that if you've got that key that you own that Bitcoin, in the case of Bitcoin, but it makes it difficult because the exchanges are the ones who really have to enforce this. You have to adhere to things like anti-money laundering laws and know your customer laws, right? So you prevent things like the Silk Road. Silk Road was an exchange on the dark web that was used Bitcoin to buy anything. You want a grenade launcher? No problem, go to the Silk Road. You want, pretty much anything. You want drugs? Go to the Silk Road. But it can scale, a very large number of nodes. It has significant performance issues, say tens of transactions per second versus tens of thousands. And in permission blockchains, you know who the parties are. They're not anonymous, they're all known, and they're all given permission to be able to participate in that blockchain. So they tend to be more centralized, but when you know the number of participants, you can use much better consensus protocols. So a little bit about Hyperledger Fabric. Any of you familiar with it? No? Okay. It's a blockchain platform developed by the Hyperledger Foundation, which is part of the Linux Foundation. So it's got good backing. They actually provide a number of different blockchain platforms. So they provide, besides this, they provide Sawtooth and a number. They also provide tools. They provide lots of different things around blockchain. Their focus is trying to get enterprises to adopt blockchain. So the way Fabric works, which is different than many of the other blockchains, is that when you want to make a transaction, you want to propose a transaction, which in this blockchain is what's called executing a smart contract. So a smart contract is nothing more than something like a stored procedure in the database. It's very similar. It's a piece of code that's going to modify some state and going to return, take some input, modify some state, and return some output. And so what happens is a client has to ask peers to execute these smart contracts. So it sends this request to several different peers. How many is based upon a policy called endorsement policy, which is basically how many people do you want to have to make sure they've got the same data so that you trust the data. And so they send these requests to the peers. They collect the responses that come back. Okay, so the responses that come back is what's called a read-write set. Read-write set is nothing more than the keys that were read and the version of those keys at the time, because it uses multi-version concurrency control. And as well, what's called the write set, which is what keys were modified and the value of the modified key, new value. That's basically what comes back from the results of the transaction. Plus, the smart contract can return some other data. But as far as what's going to end up on the ledger of the blockchain is going to be the read-write set. Once it has collected enough of these that are identical, it then submits that identical read-write set with all the signatures from the peers. So the peers sign, everything signs everything, by the way, in this environment. So the clients sign their requests, the peers sign their endorsements. So they just send that list of signatures for that block of transactions, or for that read-write set. And then the client sends that read-write set to something called the ordering service. So they do other blockchains do this differently, but in Fabric, it's execute and then order, and then actually sort of apply. So the ordering service is what's responsible for deciding what transactions go in a block. And there's different ordering services available. Some of them, are very simple, some are more complex. But the goal is the ordering service says, I put all these transactions in a block. Then it broadcasts that information to the peers. The peers then, first of all, validate that the transaction is still valid. So it checks to make sure that any keys that were read in that transaction haven't changed values. Because if they've changed values, that means it's what's called a dirty read, and you're reading stale data. And so you can get incorrect results. So if the version is not sufficient for the version number of the key that you're reading has changed, then you're going to get a version conflict, and basically the transaction is going to fail. It'll still get recorded in the blockchain, but it won't be a valid transaction. So the world state won't be changed. The world state is nothing more than a key value store that essentially is the last value of every key. So that's all the key value store that the world state is maintaining. So if it passes all that, then the write set is applied. So all the keys in the write set are updated. And then the peers are ones that are sort of responsible for the ledger. So they take the blocks, they indicate like which transactions are valid, and update the world state based upon the write set. Okay, so that's the fundamental flow in Fabric. Oracle, time-wise, Oracle in 2017 decided we would take this code and try to produce something called a managed service. So a managed service at Oracle means essentially that Oracle takes care of monitoring the system, patching, version upgrades, all that kind of stuff. I think most cloud vendors have these kinds of services where they don't just give you a VM or an image with a VM with some software installed on it. They take care of actually running it for you. So we took Fabric and made some enhancements to it and provide this managed blockchain service. An example of one of the enhancements is, remember that I talked about this version conflict, right? So if a key has been changed since it was read in the transaction, that transaction gets invalidated. Well, what we've done is we've allowed you, if you have a numeric field, it only works for numerics. We changed the write set to being, instead of writing this value, it's alter the value by this amount, plus or minus. So we just basically store the deltas. And so those can always be applied, even if the change, even if another delta has already occurred, right? As long as you don't meet some criteria, like balances don't go negative, stuff like that. But this allows you then to be able to avoid this multi-version concurrency control issue that you run into. And it's pretty substantial, because that multi-version concurrency control means that two transactions in the same block can't modify a key. Right? Because if they both modify the key, the second one is going to have, by the time it goes to get applied, it's going to have a stale version. Because the original version that they both read was the old version. Now there's a new version, so the second transaction always fails. So you can only update one key, the key in one transaction in a block. So you need to be careful about how big your blocks are. So if your block is 1 million transactions, you can have a lot of conflict. This eliminates that, but only for numeric values, which is one of the more common things that you run into. You know, somebody updates a balance of something or other. That balance could be represented as numeric, and this information stored as deltas. How to import non-XA resources. So we talked a little bit about XA resources. The resource, the database of messages, it has to support the XA protocol. So it has to be able to support prepare, commit, or rollback. You can also, though, include a non-XA resource in an XA transaction. And there are a couple of mechanisms for doing this. One is what's called the last resource committer. So in the last resource committer, what happens is the transaction manager prepares all the XA resources. And if they all agree, then it asks the last resource, the non-XA resource, to commit. If that non-XA resource commits, then it decides the outcome of the transaction is commit. If that non-XA resource fails, the commit fails, then it rolls back all those prepared transactions in the XA resources. So this is a great way to be able to include non-XA resources, not like a database or something else that doesn't support XA in an XA transaction. It does have a difficulty, though, is that when it asks the last resource committer to commit, and that fails, well, you may not know why it failed, right? Maybe it was a network failure. Well, if it was a network failure, did the request make it to the database or not? Did it make it and get applied, and you just never got the response? Well, you don't have no way of determining that, right? There's no way to go out and find out because the transaction coordinator has no way of knowing that. So there's another optimization that's done is what's called the last logging resource optimization. And what happens here is that same flow, basically prepare all the XA resources, but then it asks the logging resource to log the commit record. Remember, the commit record is the list of all the participants that are supposed to be part of this transaction and what the outcome is going to be. So it writes that commit record into the resource and then does a local commit against that last login resource. And then it can go back and say, oh, if there's a failure, it can go back and ask the LRC or the LR resource, is my log record there? My log record's there, it means it committed. The log record's not there, then it means it didn't commit. And so it rolls back all the exit resources. So you can also do this with other systems. So, blockchain by itself is great, but oftentimes you need to integrate blockchain with something else, whether that's a financial application, whether that's an ERP application, whatever it might be used with, whatever you put in the blockchain, it's not going to be everything there. It's going to be a piece of something. And so you need to integrate that. And so now the question is, how do you ensure the consistency of what you put in the blockchain with these other systems, right? So an example would be to say databases and a blockchain. So I want to take some data out of a blockchain and put it onto a database or vice versa. How do I do that in a way that's guaranteed to be consistent and atomic? And so what we do in our blockchain platform is we've made some enhancements to be able to allow the blockchain to be an XA resource. So you can specify, I want a transaction to be started here and do the blockchain updates. And then the transaction coordinator can come along and prepare that and then finally commit it. So we can support using a blockchain as part of actually multiple blockchains. These from Hyperledger Fabric blockchains, we can support atomic transactions across those. This is actually implemented as inside of what we call a REST proxy. But you can use this last resource committer to do this with other blockchains that don't have this enhancement to be able to support XA. Right? So making like Bitcoin, maybe the last resource committer, or Ethereum would be more likely the last resource committer. You could do that and still update other blockchains that do support the XA protocol. So this is the way that's done basically. So you persist the commit record locally, and then you ask the LRC blockchain to commit. And most blockchains, when you ask them to commit, they provide you a transaction ID, and you can verify it, and that's known before the transaction actually enters into the system. So you can go back and query, and you can find out whether it actually made it onto the blockchain or not. And so if it's there, if it's got the transaction, the commit record, then you get, if the transaction is there in that blockchain, you can then be sure, okay, that you're sure that it's committed. Otherwise, you roll back everything. Now, going back to transactions again, as I say, so my path here is from transactions to blockchain back. We've introduced something just last week called the Oracle Transaction Manager for Microservices. So this provides a transaction manager that supports a variety of transaction protocols. So it supports XA for really strong consistency. It supports the long running actions, and it supports trying to confirm cancel. It's basically a library, a microservice. So you deploy this typically in Kubernetes, and then client libraries that the microservices use to access it. One of the things we did, which is unique here, is that normally a transaction manager has to talk to the resource manager to ask it to prepare, commit, or roll back. Well, if you do this in a microservices world, you don't know what resource manager necessarily the participant is using, and even if you did know it, you would need the libraries to be able to talk to that resource manager, and you need a connection for that, and you need the credentials to be able to talk to that resource manager. So what we did is we come up with another mechanism where instead reuse the connection that the participant already has. And so by reusing that connection, we can simplify this and eliminate the need for RM libraries in the transaction coordinator or connections or any of the rest of that stuff. So it makes the transaction coordinator manager completely RM agnostic. Something else we do is what we call interceptors. So in interceptors, what happens is you ask the transaction manager to begin, it comes back with a header that says that you're in a transaction. When you make a call, we intercept the outbound call and add that transaction header to the outbound call. The microservice you call then intercepts the incoming request, looks at the headers and goes, oh, it's part of the transaction, and then automatically asks the participant to enlist in the transaction with the transaction manager. And then likewise, the next one that goes on. And then finally, when you go around to commit or roll back, you ask the transaction manager, and now it talks to the proxies in each of the microservices to be able to perform those RM functions. So 5 minutes, a little less now, for some reflections. And this is really quick, by the way. I hope this is helpful. So as I say, transaction processes have a long history. It gets a bad name oftentimes, but as I say, I really believe it's simply an evolution of what now we have as microservices. So we went from TP monitors to app servers to everything was SOA for a while, service-oriented architecture, and now everything is microservices running in containers. But it's still transaction processing. Something else of a reflection, by the way, this is sort of a recommendation. In any way you can, while you're in school, intern, work in your field, whatever. Okay, so you saw how much work I did as an undergrad. That made a huge difference in what I learned and how I learned information. So I could actually now see, like, why did I learn this? Why did I learn what a semaphore was? Well, when I wrote my first device driver, as an undergrad, I knew very reason why I needed a semaphore. It became completely evident. So anyways, let's say really strong suggestion is if you can work in your field or intern. And then finally, some projections. I think as people move to microservices, there's still a lot to be learned. We're sure people are going to encounter consistency problems because they oftentimes what they're doing is they're taking a monolithic application and they're decomposing it into microservices. Well, that monolithic application typically ran on an app server that provided all these services, such as transaction management services. That doesn't exist for the most part in the microservices world. We're just going to encounter, I think, a whole bunch of these kinds of things that are going to be learning experiences. I believe Kubernetes and the containers are going to essentially become the default infrastructure as a service. I think people are going to move away from VMs. There'll still be VMs, but your use of them is going to be almost always through containers at some point here. Blockchain is going to continue to evolve rapidly. I think one of my biggest concerns is, we had a hard time getting started with blockchain at Oracle because when we proposed it initially, we were pretty sure our senior executives couldn't differentiate blockchain from Bitcoin. And they are not the same thing by any means. Blockchain is a whole lot more than what Bitcoin is. And so they wouldn't approve the project the first time we proposed it. We had to go back the following year. And it's because of the hype as well. All this hype about non-fungible tokens, like the Board 8 Yacht Club stuff, whatever. $250,000 for a JPEG? You're insane. It just doesn't make any sense at all. But non-fungible tokens for real assets, like your car, your house, almost any tangible asset, a non-fungible token makes a lot of sense. Right? So I think the hype is going to be a problem because the hype is just ridiculous. And I think literally, virtually almost all cryptocurrencies are going to go away. I think they're either a combination of regulation or the central banks are going to say, enough of this nonsense. We have a currency, we'll make it a digital currency and it will be that country's currency. I'm not positive of that, but that would be my projection based upon what I'm seeing. Questions? Did I put you all to sleep? No questions? I stayed at PAR, by the way. Question though? Keep transaction processing monitor.
How does that affect the consistency of how the consistency, like how well it can do that? Because it was one of the drawbacks of this is like I think it was like Bitcoin had like certain amount of EVM and like Ethernet.
Well, CPS, which is transaction process or transactions per second. Transaction process transactions per second. I'm sorry. Yeah, that's CBS.
So I have a question. What are your thoughts about decentralization? Like you mentioned on the last point, that you think.
I think decentralization. I think there's a lot of places where decentralization makes a lot of sense. I'll give you an example of some of our customers. So a lot of our customers on our blockchain are in supply chain. So supply chain is, I want to make sure that this apple I just picked up wasn't sprayed with DDT and whatever else. I want to be able to track it. This whole farm to table kind of stuff, whatever. Well, that's a whole lot of different organizations have to come together to be able to prove that that apple came from that orchard and was carried by this truck and sold by this store or whatever. That lots of different organizations. So that's going to be a case where decentralization is sort of critical. And that's what we're seeing as the adoption of the blockchain. So there's many. Another one is Cargo Smart is a customer of ours. They provide shipping services for the cargo freight industry. So these huge freight liners or whatever. And mostly what they've been focusing on with their blockchain effort is to try to get paper stuff online and to be able to track the paperwork, because the paperwork is immense for this kind of stuff. Because you got to make sure things like, were things inspected before they were loaded? Did cargo get loaded in the proper manner or proper fashion? You don't want to put something that can explode down in the hole, because if it explodes, you lose the ship. Right? If you put it up on top and it explodes, you lose some cargo, but you don't lose the ship. And so they want to use this to be able to track the provenance, the ownership, and changes that take place in documents and stuff like that, especially say safety and regulatory. Let me go to the next first.
So in corporate setting, like how exactly does the design process work?
That's a really good question. What you look for is one of the things we talk about is looking for friction points. Okay, so where's the friction in your current transactions? We're not necessarily going to change them. We're going to change how they're being done. In the case of the supply chain stuff, sometimes it's being done just because they're purchasing packages, like our ERP package uses our blockchain for its supply chain tracking for certain supply chains. But otherwise, it's the biggest problem, I think, in many cases, is getting the business partners to come together and agree that they want to work this way, because you're disrupting how they're currently doing stuff, right? The other thing that's going to happen too, and this is an attraction for many, is that many people are using blockchain to disintermediate the intermediaries. So primarily banks. So banks, oftentimes, if you have a large contract, oftentimes what happens is you have to tell the bank that I put money in escrow to make sure I can pay for the goods that I've purchased, right? Because somebody's going to manufacture them. Well, they don't want to manufacture them unless they know I'm going to be able to pay them. So I put some money aside, but I put that in a bank, and the bank is the one who sort of manages this process. Well, they don't need to do that if you put this in blockchain, because you can verify then that the transaction that took place, the money was actually deposited. The bank doesn't have to be responsible for this. They can hold the funds, but they don't have to manage sort of this contract about has all the product been shipped? Has it all been received? Was it all received in good order? All that kind of stuff right now, the bank gets involved with before it decides it's going to release funds and something like that. So disintermediation is another thing that they would see. But the large part is really is how to adopt your existing processes into ones that make sense for blockchain. Like where do I need a single source of truth? One area that we look at is if there's any reconciliation that goes on in your processes. That's a perfect example of why I say don't use blockchain. Reconciliation means, at the end of the day, banks do what they call reconciliation, right? They check to make sure that all the deposits match all the withdrawals and all the transfers, all that stuff all matches up with the other organizations. And so the banks all exchange these messages and say, we call netting. I net owe you $1 billion because of all these transactions. All that happens at the end of the day, typically. Well, there's no reason for that. If both banks put the information on the blockchain, there's nothing to reconcile because there's only a single source of truth. Make sense?
Yeah.
Sorry.
If you were in college today, what problems or industries would you be working on or thinking about?
If I were in college today, one would definitely be consensus algorithms. There's an enormous amount of work that needs to be done there because the current ones just aren't scalable enough, or the ones that claim they're scalable enough aren't Byzantine fault tolerant, or they're making up stuff. Consensus would be one thing. Another big problem is going to be is, once you put something on the blockchain, basically it's there forever, right? Because the only way you can validate the blockchain is to be able to go through all the blocks, right? Well, 10 years from now, who's going to want some of that information? So we need to figure out ways. Now, there are things like authenticated skip lists and other stuff like that that may be able to be used to do this, but we need to figure out how to alter the current blockchain technology so we can selectively remove information if necessary. Now, it has to be done with a record of that and still be able to be a way to maintain the chains. And there've been some proposals about how to do some of this, but that'll be another area because, like I say, all these blockchains, they're just going to blow up. Right? If you're doing 100 transactions per second, how many transactions do you think that is in a year? A lot. 30 billion, I think, is it something like that? I got it just off the top of my head. And much of this information doesn't need to be stored for that long, right? There's financial records that shouldn't be stored more than 7 years or more than 10 years or those kinds of constraints. And that's something else, by the way. When you put something on you can't get it off. So things like GDPR, General Data Protection Requirements in the EU, say that you, as a consumer, as an individual, I have the right to tell a company, erase everything you know about me. Everything. Well, if you put any of that on a blockchain, how are you going to erase it? You can't change it. And we can't get rid of it at the moment. So that would be another area I think is ripe for some really good research, something around blockchain.
From like digital processes using the blockchain, and what do you think is keeping them from using
And this is the last part of that. I'm sorry.
What do you think is keeping banks from using these blockchain?
Well, every bank is doing blockchain work right now. And I think one of the areas I see this is going to take place, it's going to happen, is sort of interbank transfers, right? And so right now that's done through a network called SWIFT by most banks. It's a large network, by the way, which all runs on top of Tuxedo. And banks transfer, it's financial messaging. So they say, okay, I owe you, I'm sending you 50 million euros or something like that. And so that's how that's being done today through these messaging systems and stuff like that. I think that's going to end up, a lot of that's going to end up on a blockchain. Again, the problem is that with things like this, not being able to change the data, not being able to get rid of the data makes that a little bit more challenging.
I think we have time for one last question.
He's been waiting a lot. So.
What are the key factors that make blockchain technical possible
Compared to when it's not?
compared to the time? that makes blockchain technically possible.
Well, it's technically possible. I mean, blockchain, you know, people are using it right now, whether it's possible, feasible for a particular business application, depending on the requirements. Really comes down to, what are you gonna use this for? Some people treat it like a database that, you know, happens to have a good way to be able to make sure it doesn't get messed up or something like that. But, it's a lot more than that, you know, there's coming three folks. We talked about decentralized autonomous organization, where the put all the smarts in the smart contract, and it makes all the decisions, it does everything. Well, that's been a major failure so far, but that's the one to try.
Okay, thank you.
We guys are coming, next talk will be in 1304. Robin Bully, the key part of Coursera. We talk about CS, education. You guys are coming.
I'm sorry, what's that?
Thanks.